This video contains the solution for AP Calculus BC 2009 Form B number 5. And there's a graph involved, so take a look at that. So let's see, we have g is a continuous function, and right away I'm going to note that they're talking about g here, and this is the graph of the derivative of g. Talking about the g function here, but this is its derivative. So let's make sure we note that. So g is a continuous function with g of 2 equals 5. Notice that the point 2,5 is not on this graph. This is the derivative. The graph of the piecewise linear function g, so they're just telling us those are straight lines, is shown above from -3 to 7. They want us first in part A, find the x-coordinate of all points of inflection of the graph of g of x for in between -3 and 7, and justify your answer. Well, let's see. Points of inflection when do points of inflection happen? They happen when the derivative, let's see here, they said points of inflection of the g function, right? Which is not pictured. When g prime goes from increasing to decreasing, or in other words, when the second derivative goes from positive to negative, or negative to positive. In other words, where the second derivative changes sign. Remember, it's not just where the second derivative is equal to 0, it's where it changes from positive to negative. So let's see. If we're given the graph of g prime, we want to know where g double prime, or in other words, the slope of this, goes from increasing to decreasing, or vice versa. Well, it says increasing, increasing, then decreasing, and then increasing. Another way to look at it is the maximums and minimums on the derivative are the inflection points. That's also another way to look at it. So that happens at 1 and 4. X equals 1 and x equals 4. And I think we've got the justification here. Part B, find the absolute maximum value of g on the interval -3 to 7. So that's not this or this, right? This is the g prime function. Let's see if we can figure that out. The absolute maximum value of g on that interval. Well, this is the derivative. So this function is decreasing, then increasing a bit, and then decreasing, and then increasing a bit. So if we want to find the maximum value, we've got to figure out where it's, well, we don't need to figure out where it started, but from here to here, if we want to know how much the original function changed, then we're talking about area, right? So amount of change is equal to area under the rate of change. So it looks like this area is -4, right? That triangle, and then inside this triangle here, that would have an area of positive 1.5. So far, this function here, it started here and then it went down 4. We're talking about the original g function. It went down 4, then up 1.5, then down 4 again, and then up 0.5. So if you follow, if you think about that, we started somewhere, wherever, and we went down 4, up 1.5, down 4, and then up 0.5. So the maximum value is actually right here, because we started off over here and then we did mostly decreasing from there. We never made it back up to that original height. We decreased, increased a little, decreased some more, increased a little. That's the maximum value. So, absolute maximum value of G. Oh, they want the actual maximum value. Well, let's see. That means we need to actually find some area here, because we know the one point that we do know is that G of 2 is 5. So let's see. We know that the max is at x equals -3. So let's see. The integral from -3 to 2. -3 is what we're interested in. 2 is what we know of G prime of x. X is equal to, see, the area from here up to 2, that's -4 plus 1.5. -4 plus 1.5, which is -2.5. And that would be equal to the antiderivative of this. That's G of x. So that would be G of x from -3 to 2. And focusing on that part of the equation right here, it's going to be -2.5 is equal to G of 2, which is 5, minus G of -3, and that's the maximum value that we're interested in. So subtracting that over to, oh, actually, let's add this and then add that. So it looks like G of -3 would be equal to 7.5. That is the absolute maximum. And they want us to justify our answer. I guess we could say something like, because after x equals -3, the g function decreases and never makes it back up to that value, 7.5. You can check their rubric and see what they say about that, but I think that would be perfectly good justification. And let's see, find the average rate of change of g of x on the interval from -3 to 7. All right, average rate of change. Well, let's see. Average rate of change would be the slope. That would be g of 7 minus g of -3. That's y minus y over 7 minus -3. And let's see, how are we going to get that? Well, let's see, we can get that by doing doesn't that look like the fundamental theorem plugged into this, right? G prime, that area under G prime of x from -3 to 7, well, that would be G of x from -3 to 7, and that's G of 7 minus G of -3. That's exactly what we're looking for there. So we need the whole area under the whole thing. That's the -8 plus 2, that's -6. And then if we want to find that average rate of change, we also have to divide by this. So that would be -6 divided by 10, or -0.6. And notice here, if you see what's happening, this looks all of a sudden, you're like, wait a minute, that was the average value of the derivative. Well, this is the rate of change. So another way to think about this, conceptualize this, is it's the average of the rate function. So we actually went back and found this and then divided by exactly like we were doing slope of a secant line, but you could also think of it as the average value of the rate function, and that would get you to the same place. We just divided by the 10 afterwards instead of putting the 1 over b minus a in the front. So either way, negative 0.6. And last part, D, find the average rate of change of g prime of x on the interval. Well, this is g prime of x, so if you want the average change of the function you're actually looking at, you just have to connect the dots, right? We have the secant line right there. It's just, let's see, g prime of 7 minus g prime of negative 3 over 7 minus negative 3. And so that's, let's see, 1 minus negative 4 over 10, so that's 1/2. Now, does the mean value theorem applied to this interval guarantee a value of c for negative 3 such that g double prime, in other words the derivative of that, is equal to this average rate? Why or why not? Well, remember what the mean value theorem says. Applied to this function, the mean value theorem would say that if this function is differentiable, in other words, if it's a smooth curve with no sharp corners, then somewhere there must be a value in this interval where the average slope is equal to the slope of the tangent line. And that does not apply here. Think about that for a second. Maybe pause and come back and you can write down why. So why not? Because this does have sharp corners, so the mean value theorem does not apply. It turns out there actually is a spot where the slope of the tangent line of this is equal to the slope of the secant line, but not because of the mean value theorem. It could easily have had a different slope and never been equal to, it could never have had a spot where the slope was exactly 1/2. It just so happened that one of those line segments did have that slope, but that was luck. So no is the answer. And why? Because because g prime of x, that's the function we're talking about here, is not differentiable on that interval from negative 3 to 7. It only takes one sharp corner in that interval to make the mean value theorem not apply.